have access to it. And I'm trying to see if I can stream it on YouTube so that it will be there for use. Hold on, coming. I just record from here. Let me show the slide from the back because of people who are going to get the recording. I forgot to start the recording on time. So we are talking about effect of radiation on growth. This and this. Okay. Effect of hydrostatic pressure on microbial growth. When we say hydrostatic pressure, we're talking about the pressure at the depth. We're talking about depth of an environment. So what is the effect of the hydrostatic pressure in this case? Naturally, pressure inhibits the growth of microorganisms, except other organisms that probably live in environment that are, deep down, like in the ocean. So pressure inhibits their growth, it makes them to grow less. So many organisms are never subjected to pressure in excess of 1 atmosphere, which is equivalent to 101.3 kilopascal or higher. So during higher pressure, there is usually an interference with protein synthesis and energy transfer from catabolic biosynthetic system, which is observed. And this usually results to inability of the organism to adapt to new substrate, especially when we're talking about the log phases. During the log phase, when the organism is trying to adapt to the new substrate for fermentation process, when the pressure is much, rather than the organism focusing on how to metabolize the substrate, the organism is battling with stabilizing its own cell. So the organism is unable to carry out the primary function because the organism is trying to survive the pressure. If you notice, if you yourself, when you are on an elevator and the elevator is descending, you know how it does your body. It does your body somehow. See if you are weightless, and some people can cling on something if that's the first time riding an elevator. Now, this same pressure is also seen in the microbial cell. It interferes with their protein synthesis. Remember, microorganism has only one cell. So whatever happens to the cell happens to the whole body. To the whole cell. So, for example, in cider production, yeast performance is impaired when fermenter depth are greater than 14.5 millimeter, which produce hydrostatic pressure. So, for fermentation process, where we see the pressure is at the particular part where we have the fermenter. The fermenter situation determines the pressure that is being exerted on the organism. So when the fermenter depth is too much, it affects the fermentation processes. So that means when a fermentation jar is situated, it must be on a level ground, not that at the depressed part of the industry, not at the like maybe an underground. So it is not suitable for fermentation to be situated at the underground part of the industry, because at that time it is below the ground level and there's a pressure that is exerted, and these have effects on the organism. However, many marine organisms must be barotolerant. They are barotolerant because they live at depth of ocean where pressure is more than the surface. So such organisms, they have adapted to higher pressure than organisms that are living above. They don't survive higher and lower pressure. They are adapted to the lower pressure. So it's a balance of nature, but it's not all sorts of organisms that are used in the industry. For industry where such organisms are used, then artificial pressure is allowed to stimulate their environment for their productivity. Some of them even grow better under this condition, and they are truly barophilic. They love higher pressure. They are capable of living under 700 to 1,000 atmosphere. And you know, other organisms can only survive 1 atmosphere. If it's more than 1 atmosphere, they will not survive. And these organisms, they will not even grow at 200 to 600 atmosphere. How much more 1 atmosphere? And some other organisms, they will not grow when it's above 1 atmosphere because of the hydrostatic pressure. It affects their growth, while the marine organism, they embrace the higher pressure because it enables their own growth due to adaptation to depth of the ocean where they are found. The control or inhibition of microbial growth. So how do we control microbial growth? We are gradually rounding up. The control or prevention of microbial growth is necessary in many practical situations, particularly in healthcare, food processing, and preparation and preservation of material. Control can be achieved using physical or chemical agents that either kill microorganisms or inhibit their further growth. We are talking about controlling microbial growth in the environment where fermentation is being carried out. If you don't control the microbial growth, you're going to get contaminants in your production, and your product is going to be badly affected. Your contaminant is going to compete with your organism for nutrient supplements, and the organism, if care is not taken, if it's not a fast-growing organism, the contaminant outgrows them, and you end up wasting all the resources in getting nothing. And most of the time, some of these contaminants can have a similar growth-like features, but unable to produce the metabolite. So there's a need for control of the microbial growth in the environment. That is why we talk about radiation. Radiation is used in sterilizing the environment, but care must be taken to avoid radiation interfering with the growth of the specific target organism meant for the proper fermentation process. So sterilization procedure completely destroy or eliminate all viable organisms. You're very familiar with sterilization process and your 200 level. So sterilization process are used in ensuring that microorganisms are removed from this environment. It eliminates viable organisms, including their spores, or it may be performed using heat, radiation, and chemical. Now, the particular method of sterilization to be used is a function of the environment. Definitely, you cannot use boiling, you can't use autoclaving for sterilizing the environment of the industry. So definitely, such methods like radiation are used, okay? Some chemical disinfectant are used, and the physical removal of washing, cleaning using disinfectants are used. Sometimes hot air are blown, but these are not common methods, okay? They are not common methods, but radiation, chemical use, and physical removal of cells are used in controlling microbial cells. So these methods, I believe, frankly, that you all understood these methods of controlling microbial cells. If I ask you in your exam that describe the method of controlling microbial growth in the industry, you should be able to expand on this. And don't give me a slide. If you give me a slide like this, definitely you know your score is 0. You know that. So I'm just giving you an heads up. I'm not saying I'm going to ask you this question, but if question like this is asked, you are in foreign level, you are expected to tell us how do we control that? What are the specific methods? What are the applicable methods for controlling microbial growth? Talk about radiation, talk about application of chemical disinfectant, physical removal of cells, not autoclaving, not flaming, not other conventional laboratory method. You know, it's an industry different from conventional laboratory method. So factors that influence the effectiveness of any microbial treatment. So when we are talking about who is that person, please don't disturb our class. I will remove you immediately and I will mark you. So factors influencing the effectiveness of any microbial treatment We are talking about population size. If the population of the organism is too much, it can affect the antimicrobial treatment. Antimicrobial treatment, now we are talking about antimicrobial treatment, not antimicrobial drugs, not antimicrobial substances. We are talking about treatment that is antimicrobial in nature. So if the population of the organism is too much, so that means you might have to increase on the treatment. If you don't, you will not get a clean environment. The population composition is also critically important because for population composition, if it's a mixed community of organisms, some could be susceptible to some treatment, some may not be susceptible to some treatment. So the treatment methods cannot be generalized because some of these organisms have higher tolerance and higher resistance level to certain treatment. This is a factor that influences effectiveness of antimicrobial treatment in the environment, and the concentration of the antimicrobial agent or the intensity, the concentration in terms of the volume, maybe radiation, what is the wavelength that you're using, or the duration. And in terms of antimicrobial agents, what are the concentration of the chemicals or intensity of the treatment. This is a factor. You must not use sublethal concentration in cleaning the environment, and you must not use low radiation when you're expected to use higher ionization energy. The period of exposure to lethal agent, that was the time period to be used. You know, the time period, the time frame, the contact time for chemicals, maybe the chemicals supposed to be applied and supposed to stay for 1 hour, because some organisms can tend to resist to the point at which maybe their growth is not stopped. So what is the contact time? The contact time is very important because the time kill studies shows that at 0 time, only few organisms dies at the contact with chemicals. So at 30 minutes, how many population dies? At 1 hour. So these are experimental procedures that have been carried out successfully and optimized to the point at which you know the appropriate period to which contact with the chemical will totally eliminate a certain population of organisms. So it could take up to 3 hours, it could take up to 4 hours, or 1 hour, depending on the potency of the chemical. Then temperature must be properly regulated, otherwise it could also have negative effect in delivering effective treatment. Environmental conditions such as pH, medium, viscosity, and the concentration of organic matter present in the environment are also important factors that can also affect microbial treatment. So the growth kinetics. Growth kinetics is represented by this equation. Remember, we were talking about the growth during the monitoring of microbial growth. Then what about the growth by log phase, lag phase, then stationary phase? Lag phase, log phase, stationary phase, and decline. So there's a growth kinetics that is used in determining the microbial growth. So the equation for growth or binary fission of organism is given as B equals to B times 2N, where small letter b, the small b, is the number of bacteria at the end of a time interval, while B is the number of bacteria at the beginning of the time interval. N is the number of generations. So that is the number of times the population doubles in the time interval. So if we get a logarithm of both sides, give me log B small and log B capital and n log 2n. This will give us, looking for the factor n, to get the number of generation, and we carry out the logarithm of both sides. It will give us n log B minus log B over 2 log 2. So, and log 2 is this, 0.301. So dividing that gives you n equals to 3.3 log B. But generation time is equals to T over n, whereas the n is 3 log B over B. So therefore, generation time during the growth kinetics is given as time T over 3.3 log the initial number of the bacteria over the total number of bacteria after the time interval. So this formula must be applied for every calculation that is being given for calculation of growth kinetics. Unfortunately, we are not having physical class. We'll try and see if we can have some examples to solve. The example is not programmed on my slide, but you can have something to practice because most likely you may have to do some calculation. So media formulation and economics. Media formulation in industry is an essential process that is used in ensuring proper growth of organisms for fermentation. They are essential for propagation and fermentation of microbial cells for desired product or target. Media are formulated in such a way that it must contain the nutrient that will support and promote the synthesis of the target product, either cell mass, cell biomass, or a specific metabolite. So in fermentation, the most suitable type of media is liquid media. In fermentation process, the most suitable media is liquid media. Obviously, we can't use solid media for fermentation. It can be used, but it's not suitable. Although some solid substrate method fermentation are used, but the most suitable one is liquid media. So in most industrial fermentation, there are several stages where media are required. That is when media are constantly introduced. We have the inoculum stage. This inoculum stage requires media because this is the starter culture part. Then we have the propagation step. We also have the pilot scale fermentation, and we have the main production fermentation processes. Where biomass or primary metabolite are the target product, the objective is to provide a production medium that allows optimal growth of the organism. I mean, if the biomass or primary metabolite are the target product, so your objective is to provide a medium that will allow the best form of growth of the organism. So for secondary metabolite production, such as antibiotics, their biosynthesis is not growth related. Consequently, this purpose media are designed to provide an initial period of cell growth, initial form of cell growth, which is followed by conditions such as optimized for growth for this same secondary metabolite. So, at this point, the supply of one or more nutrients, such as carbon, phosphorus, or nitrogen source, may be limited and the rapid growth ceases. So, the initial step in media formulation is the examination of the overall process based on the stoichiometry for growth and product formation. This primarily involves consideration of the input of the carbon and nitrogen sources. I said the initial step in media formulation is to examine the overall process based on the stoichiometry for growth and product formation. This primarily involves the consideration of the input of the carbon sources, nitrogen sources, mineral, and oxygen, and their conversion to cell biomass, metabolic products, carbon dioxide, water. It's what we're saying here. We are looking at all the media availability and what is their contribution. How are they going to lead to the production processes? We want to look at the carbon sources, is it enough? The nitrogen sources, is it adequate? The mineral, oxygen, because all these are required for the organism to provide metabolic products, or if it is cell biomass that is to be harvested. So the concentration of these are very critical for fermentation process. So for carbon sources, it serves as energy source in most fermentation process. It's one of the most important requirements for all biosynthesis, leading to reproduction, product formation, and cell maintenance. So carbon sources is critically important. So carbon sources can be obtained from different sugars, such as mannitol, sorbitol, organic acid, fatty acid, protein, peptide. Now, there's a point I missed earlier. When we say media economics, media economics is like we are looking for the best media to give us the desired product. So we are trying to look at all the sources available for carbon sources. Which one is the cheapest? Which one is the most expensive? So which one is going to be the most suitable for this organism? It's like looking for delicacy for the organism and looking at the cost. Some of these delicacies can be, I mean, different in terms of cost, but it's going to come down on the same nutritive value for the organism. So you have to select the best of all and the most affordable so you can make your profit. Simple carbohydrates. So simple carbohydrates, we have simple sugars, which are semi-purified polysaccharides, sugar alcohols, and all that. These are simple carbohydrates that are used for fermentation processes. We also have complex carbohydrates. Complex carbohydrates such as starch, corn, rice, meal, or wheat, potatoes, etc. are a source of starch. Cellulose, corp, straw, wood, they are also carbohydrates, but are complex. They are different from simple carbohydrates. Simple carbohydrates are just smaller carbohydrates that contains molasses, corn molasses, beet molasses, liquor, and all that. Carbohydrates are traditional carbon and energy source for microbial fermentation, although other sources may be used, such as alcohol, alkane, and organic acid. Molasses. Molasses are alternative supply of pure glucose and sucrose. Now, I was telling you that we need to look at the best sources to replace the most expensive ones. So molasses are alternative to glucose. Glucose and sucrose, they are delicacies for microorganisms, but they are very expensive for a large-scale fermentation processes. So the high cost is going to prevent their usage. So there's an alternative source, which is molasses, which is a byproduct of cane and beet sugar during production. So it's a cheaper and more affordable source of sucrose instead of using the sucrose itself. Sucrose is still going to give the same sugar, but it's more expensive. So molasses is the remainder of the residue remaining after most of the sucrose has been crystallized from plant extract. So this can be used for replacing glucose or sucrose. Malt extract is obtained from barley during the process called malting. So they are also useful carbon sources for the cultivation of filamentous fungi, yeast, and actinomycetes. This set of organisms, they find delicacies in malt extract. So they won't grow if we don't. They will grow, but we are talking about optimal growth. So optimal growth needs to be put into consideration. It's not enough for your organism to grow, but the organism must grow optimally in order for you to have the best of the organism. So they are useful for the cultivation of the said organism. The composition varies to some extent, but they usually contain approximately 90% carbohydrate on a dry weight basis. So this comprises of 20% exosis, and these are the formulas. Anyway, starch and dextrins. Dextrins are made by eating dry starch with or without acid. So like other converted materials, this product offer a way to use higher solid to increase performances. So dextrins differ from fluidity starch in that they Their cold water solubility increases while their gel strength and their mean molecular weight are reduced. So dextrins are another form of alternative to using direct starch. Dextrins are more completely hydrolyzed product than fluidity starch. So instead of using starch, dextrins provide you an alternative. Starch is also, as you know, is very expensive, though the organism needs starch. We are talking about starch casein, starch in media, and we are looking at a large production. So dextrin is giving the organism the same delicacy, but from a different source, and it provides the same nutrition. These polysaccharides are not as readily utilized as monosaccharides, and that's why, but can be directly metabolized by amylase producing microorganisms, particularly filamental fungi. So their extracellular enzyme hydrolyze the substrate to a mixture of glucose, maltose, and maltose to produce a sugar spectrum similar to that found in many malt extracts. So it's going to give you the same product. I mean, the same delicacy, so to speak. So, and it's on a cheaper side. And the goal of every industrial microbiology, like I always tell you, is to drive your process through the most economical way and get the best product for use. Cellulose. Cellulose is predominantly cellulose is predominantly found as lignocellulose in plant cell wall, which is composed of three polymers: cellulose, hemicellulose, and lignin. So few microorganisms can utilize it directly, as it is difficult to hydrolyze. However, it is potentially a very valuable renewable source of fermentable sugars once hydrolyzed. So cellulose is one of the renewable sugars that can be used for fermentation process, especially in the bioconversion to ethanol for fuel use. So cellulose can be presented to the organism; they will not be able to completely exhaust it. And the organism, they need sugar. So cellulose can provide this renewable sugar for this organism while fermentation goes on, and it can last longer. Whey is an aqueous byproduct of the dairy industry. It is expensive to store and transport. Therefore, lactose concentrates are often prepared for later fermentation by evaporation of the whey, following removal of milk protein for use as food supplements. So lactose is generally less useful as a fermentation feedstock than sucrose, as it is metabolized by fewer organisms, such as Saccharomyces cerevisiae, for example, does not ferment lactose. So whey is an aqueous byproduct of the dairy industry, which can also be used, though it is a bit expensive to store and to transport. So sometimes it could be generated on site for use during fermentation process. So we have the alkanes and alcohol, which are also methane products of hydrocarbon, which are utilized as carbon sources by few microorganisms. So because these are basically carbon too, they have carbon sources. So some microorganisms can use these for their bioconversion processes for products. It has a high miscibility with water and high carbon content, plus it is relatively cheap. So these products are relatively cheap and can give this organism the most suitable nutrition, substrate for carbon source. One drawback is that only a limited number of organisms will metabolize it. So not all organisms can utilize these methane product, but for those that can utilize it, it is one of the most cheapest source for carbon. Ethanol is less toxic than methanol and is used as a sole or co-substrate by many microorganisms, but it is too expensive for general use, such as for carbon use. So we have second to the last, which is the nitrogen sources. So nitrogen sources are critically important in the fermentation process because nitrogen also play a critical role in the fermentation process, as an energy supply, no, not, as a cellular growth substances. Microorganisms depend so much on nitrogen for their DNA, for their RNA, for the protein and all that. So nitrogen is often supplied in crude forms that are essentially byproduct of other industries, such as corn stip, liquor, yeast extract, peptone, and soya milk. So most of the industrial microorganisms have the ability to utilize both organic and inorganic nitrogen sources during fermentation. So yeast extract is one good sources from nitrogen, usually used as a growth stimulant or growth factor. Is a direct product, direct component of nitrogen. So it is essentially needed for growth during fermentation process. So they are good additive for the microbial growth. They may be produced from waste baker and brewer yeast or other strains of cerevisiae. They are also obtained from waste from wood and paper processing. So when you get something from waste, you're not going to buy it. You only need to look for a way of extracting it. Instead of you going to the shelf and purchase some large quantity. So after purchasing all this large quantity media and you want to sell your product, you are going to look at the cost of these sources of nutrients for the organism. And these costs are directly linked to the kind of product, the cost, because you are not going to run at loss. When you provide media with less cost, then you'll be able to sell your product at an affordable rate. And this is the goal of every industrial microbiology. So I'd like to inform you that we have come to the end of the class with me. Congratulations for your. Next time, Dr. Brahma will be the one to teach you. And I'm going to contact you to inform you when we are going to do my second test. We actually did one test. We're supposed to do up to 3 tests. But we've done 1, so I'm going to reduce it to 2. So I'll let you know maybe next week or in 2 weeks' time. It won't exceed 2 weeks' time. So we are going to do the tests on your LMS. And make sure you get a very good internet facility. Make sure you are prepped to it and don't give me an excuse. Okay, if you have any question, please say it now. If you have any question, I will unmute you or unmute yourself and ask a question. If you don't have any question, I ain't got more time. If you have any question, let us hear it. Maybe you are all sleeping. Are you all sleeping? Are you there? Are you all there? Olalade, okay. Are you in the class? Olalade, okay. Are you in the class? Ololade, okay. Are you in this class?
I'm here.
Are you sure? Is that your voice or somebody is speaking on your behalf?
I'm here.
Okay. All right. You have any question for me?
No, I don't.
That means you understand everything. Who is shouting Mayowa there in your house? That means you understand everything, right? Well understood. Right?
Well understood. I'm going to read it more if I have time. I'm going to read it more. I came late to the class, so I wasn't there from the beginning.
Okay, we waited for you. We waited. So it's all right. Go and read. I implore everybody to go and read. I'll send this slide to you guys. I will upload it on the YouTube. And I was trying to stream it. I didn't know that I didn't enable it. But that's okay. I'll upload it manually. Then This is the last time we'll be having this conversation with your class. Next time will be probably in the examination. I wish you all good luck, best of everything. We may not see again, until exams. So I wish you the best. See you at the other side.